In this video, we're going to be starting to lay some of the very important and basic foundation for what we need in the more advanced videos that will follow. So this video will be concerning the Cauchy-Riemann equations, which are a set of equations of complex analysis that deal with differentiability and continuity of complex functions. So I've written a lot of things already for this video because there's a lot of information, so I want to try to get through it as quickly and concisely as possible. So first, we're going to talk about a few definitions. So first, the definition of differentiability. So f is differentiable at z0 in the domain in which it is defined. So D is the domain of f. So it is differentiable at z0 if limit as z approaches z0 of f of z minus f of z0 over z minus z0 is equal to, and this is just another definition of the limit, so these should be familiar from single variable calculus, which is why I'm not going to go over them too much. So just instead of using x's, we're using z's because this is complex. So if this definition of the limit, so this is one definition of our limit, and this is an alternate definition which should hold true as well, and they should be equal. So this one is the h definition, where you have limit as h approaches 0 of f of z0 plus h minus f of z0 over h, and that approaches some number. So the important thing to note here that's different from real variables is that this h is complex, where before we had h is just in one dimensional, it's x plus h. This is z plus h. And just to make a quick sketch, if this is the complex plane and this is our z0, h can be anything. It can be in this direction, this direction, this direction, this direction. And the consequence of that is that when we put limit as h approaches 0, we need to have it approach 0 from every direction. So for example, in this direction right here, we need to have it approaching 0. Let me use a different color. It needs to be approaching 0 in this direction. In this direction, it needs to be approaching 0 like this. So it needs to be approaching 0 from all directions. And furthermore, the limit from all directions must be equal, which is something we stressed in the limits video. Okay, so if these two limits, which should be equal, exist, then f is differentiable at z0, which is in the domain. And that derivative, which we'll call, is denoted by f prime of z0, which you might think that makes sense. So just very important to note, the key point of this is that this h must approach 0 from every direction, and we'll see why that's important soon. Okay, so now a few more definitions. If f is differentiable at all points of its domain, D, it is called analytic. Very important word to know. Now, another definition, if f is differentiable on the whole complex plane, then it is called entire. So this might make a little bit of sense because entire, like entire complex plane, for example. Now we just have to go over a few rules, which are similar to real variables, so they shouldn't be that hard to memorize. F plus g, so in all these brown examples right here, we're assuming that f and g are analytic functions on a domain D. So if that's true, so if f and g are analytic functions on the domain D, then f plus g derivative is equal to f prime plus g prime. Fg prime, so this is multiplication. We use the product rule just like before, so it's going to be f prime g plus g prime f. F divided by g prime, we can use the quotient rule, so it's going to be bottom times derivative of the top minus top derivative of the bottom all over g squared. But important thing to note here is that this must be so that g of z0 is not equal to 0. And z0 is just the point that we're taking the derivative at. And that makes sense because if it's 0, then we have a denominator 0 and things kind of break down. So just make sure g of z0 is not equal to 0. And this last one is the chain rule. So that's also like single variable. So we have g of f of z and we want the derivative of the whole thing. So it's going to be g prime of f of z times times f prime of z, okay? And that's just the chain rule. So these four things, keep in mind, they shouldn't be that hard to memorize because they're the same from real variables. So hopefully you'll keep that in mind. So polynomials are always entire. So these are polynomials in terms of z, right? So an example would be 2z cubed plus 5z plus 3. This is a polynomial in terms of z, where z is a complex number. This is always entire. So it's differentiable everywhere on the complex plane. Rational functions, which are the quotient of polynomials. So let's say r of z equals p of z over q of z, where r is a rational function. This is always analytic. Analytic on any domain without a 0 of q of z. And the reason for that is the same thing as why we had to have q of z is not equal to 0 here, because if we put it on a domain that contains a 0 of q of z, then this will be equal to 0, and then it won't really be differentiable. So this is always analytic on any domain without a 0 of q of z. Okay? So now just a quick other thing to note. If f of z is analytic on D, what about g of z, and so this is just another function, equals e to the power of f of z? Well, it turns out that is also analytic on D with a derivative what? So we can just apply the chain rule here. So g prime of z, it's going to be e to the f of z times f prime of z. Okay? So I put this here because we're going to be using this in proofs or future videos. Okay? So now, finally, we have arrived at the Cauchy-Riemann equations, the main point of this video. So what's going to follow in this video is 3 theorems, Theorem A, B, and C, and the proofs can be kind of long, so I won't include them in this video. I'll be including them in a separate video. So at the end of the video, I'll link to the proofs. There'll be 2 or 3 proof videos for each of these theorems. Okay? So Theorem A, and this is Cauchy-Riemann equations. So suppose a function f equals u plus iv, and if we haven't gone over this notation before, u is the real part of the complex function and v is the imaginary part of the complex function. But u and v are both real valued functions. So that's important to stress. Real valued functions. And this I takes care of the imaginary output of this f. Okay, so f equals u plus iv is analytic on D. So that's what we're going to suppose. Suppose it's analytic, so it's differentiable on all points of D. Then, in D, these relationships hold, and these are the actual Cauchy-Riemann equations. So partial derivative of u with respect to x equals partial derivative of v with respect to y, and partial derivative of u with respect to y equals negative partial derivative v with respect to x. Okay, so these are the relationships that hold if it's analytic on D. And again, the proof, in fact, I'll just link it right here. So click right here for the proof to Theorem A. Okay, so now let's go right into an application of this to see why this is useful. Because on the surface, you might be thinking, why is this useful at all? It just looks like very weird relationships. So here's why. So we're going to suppose that some function f equals u plus iv is analytic on some domain. Okay, and we're given that we're given u straight up, u of xy is equal to x squared minus y squared. And again, this x and y are just the real and imaginary parts of z. So that means z equals x plus iy. Just a refresher. So we're given the u. We want to find v of xy. So it seems impossible without these equations. So let's just go right into it. Let's first write the 2 partial derivatives of u. So du dx partial is what? That's going to be 2x. Okay? Now du dy is what? Negative 2y. Now we're going to use the Cauchy-Riemann equations because du dx is what? It's equal to dv dy. So dv dy equals 2x as well. And dv dx is what? The negative of du dy. So that means dv dx is equal to 2y because this was negative, so this is positive. Okay, so now what can we do? Now we can rewrite this dv equals 2x dy. This is a 2. Dv equals 2y dx. Now we can use integration or just observation with integration to figure this out. So I carried out our integration, and so we have v equals 2xy plus phi of x, and v also equals 2xy plus psi of y. So if you're not familiar with this psi or phi notation, these are just functions, and this is just a function of x because let's say we did dv dy on this, we would get 2x, and this would just go away because this does not include y. And on the same page, if we did dv dx here, this would be 2y plus, and this would go away. So we have to include this function of y here and a function of x here when we're integrating with respect to x and y respectively. Okay, so now all that's left to do, we just equate the v's. So this 2xy is common, and we don't see any function of x or y that's common, so these are just 0. So our final answer, and I'll write it in red, let's say, we have v of xy equals 2xy, and we're not exactly done, we have to include plus c. And c is what? C is a real constant. So it's a purely real number, and that has to be there because if we integrate this with respect to v, with respect to x or y, this constant will go away. So there's a lot of different v's really. We can have 2xy plus any real constant, 1, 2, 3, 4, any real number that we want. The reason it can't be an imaginary number is because v, again, we said is real valued. Okay, so that is an application of the Cauchy-Riemann equations. It helps us to find v given u, or u given v. So now the next thing we'll talk about is harmonic functions. So I've written here second derivative partial of u with respect to x, second derivative partial with respect to u of u with respect to y, and we're adding them together. So this looks kind of messy, but let's try to break it down. So we have d dx of du dx plus d dy of du dy. And now what we're going to do is we're going to rewrite this du dx and du dy with the Cauchy-Riemann equations. So we get d dx, and remember, du dx is equal to dv dy, dv dy plus d dy, and remember du dy is equal to negative dv dx, negative dv dx, and now we're going to write d squared v dx dy minus, because there's a minus here, d squared v dy dx. And if you remember from multivariable calculus, whether you have dx dy or dy dx, so whether you take the partial with x first or y first, it doesn't matter as long as this thing is continuous. So this is really the same thing, and this equals 0. So what do we find overall? We found that this first thing is equal to 0. So we found that, I'll write this in a different color. So we found that d squared u dx squared plus, and this is called Laplace's equation. And any function, so for this example was u, that satisfies Laplace's equation is called a harmonic function. So that means u is a harmonic function. And furthermore, something to note is that any v, so any v that satisfies the Cauchy-Riemann equations with that u. So first of all, we have u, which is a harmonic function, and if we choose that u in our Cauchy-Riemann equations back here, so here are our Cauchy-Riemann equations, if we find a v that satisfies, that works with that u, so that this equals this and this equals this, that v is denoted as the harmonic conjugate of u. So again, to recap, a harmonic function is something that satisfies Laplace's equation here. A harmonic conjugate of that function is something that satisfies the Cauchy-Riemann equations with that harmonic function. So harmonic conjugates will be useful a little bit later on, but it's good to introduce them right now. So next thing we're going to do is just introduce a theorem. We're not going to apply it, but I will give a proof. So this is called Theorem B. So first we suppose that f equals u plus iv is analytic on a domain D. So if u is constant on D, or u squared plus v squared is constant on D, then f is constant on D. So this is something of a surprising theorem, because you wouldn't think that just having u constant means that u plus iv is constant, because what does u have to do with v? Well, the answer is the Cauchy-Riemann equations, because u and v are linked if f is analytic on D. So I will give a proof of this. We will use it. This is actually something we'll use for proofs later on, which is why I put it here. But let's just jump right into Theorem C, which is the last topic of this video. Theorem C says, again, suppose that f equals u plus iv. So f. Suppose f, u, v, and all the partial derivatives are continuous, okay, not differentiable yet, are continuous in a disk centered at z0, z0. So just to recap what that means, here's a complex plane, here's z0, here's a disk. Okay, so if they're continuous in there, so suppose they're continuous in that disk if u and v satisfy the Cauchy-Riemann equations at z0. So at z0, if these relationships hold right here, then f is differentiable at z0. And furthermore, we're given the derivative f prime of z0 is equal to partial derivative u with respect to x, plug in x0, y0, plus I times partial derivative v with respect to x, plug in x0 and y0. So I will again, of course, give a proof for this. So for the proof to Theorem B, click right here. For the proof to Theorem C, click click right here. Okay, so last thing we'll do is apply this. So let's do a slightly involved example. So I'll do it here in blue. Suppose D is a domain with a single valued branch of log Z. So go back to the log video if you need a refresher on log. We want to find the derivative of log Z. So what's our initial guess? We might think it's just, if we have real variables, it's 1 over Z. And that's going to prove to be correct, but we have to prove it. Okay? So alright, this is our guess. So now what? So now what's our first step? So let's write down log Z as we know how to write it. So log Z is equal to natural log of modulus of Z plus I times theta. And remember that theta was, so this was Z, the complex number. Theta was the angle here, right? Okay, so now let's write this in terms of x and y. So if Z equals x plus IY, this is natural log of x squared plus y squared to the 1/2 power. So remember, square root of x squared plus y squared is modulus of Z. That's how it's defined. Plus I times arctan of y over x. Because remember, if we want this theta, we want to do arctan of rise over run, so slope basically. So y over x. Okay, so now we have in terms of x and y, we can play with a little bit. So first thing I want to do is take this 1/2 down, which is rule of natural log logarithms. So x squared plus y squared plus I inverse tan y over x. Okay, so now what's the next thing I want to do? So now, notice we put this into a f equals u plus iv form, because this is our u and this is our v. Because notice they're both real valued functions, and the v is the imaginary part because it has an I sticking in front of it. So this is very good, because now we can start looking at, are the Cauchy-Riemann equations met? So du dx is equal to what? So du dx is going to be x over x squared plus y squared, and then we're going to have du dy equals y over x squared plus y squared. dv dx equals negative y over x squared plus y squared, and dv dy is equal to x over x squared plus y squared. So how I got these, the ones with the u might be more simple because it's just a simple matter of doing 1 over x squared plus y squared and doing a chain rule. Inverse tan derivative, go over it if you forgot it, but this is just the inverse tan for real variables, and you have to do a little bit of chain rule, a little bit of partial derivative work, but it turns out this is what you get in the end. So du dx, du dy, dv dx, dv dy partial. So now, are the Cauchy-Riemann equations met? Let's go back to the Cauchy-Riemann equations. So Cauchy-Riemann equations are du dx equals dv dy. Is that true? Du dx, dv dy. These are indeed the same. And the other part was du dy is the negative of du dx. Is that true? Yes, the negative sign is there. Indeed, these are true. So that means Cauchy-Riemann equations are met. Okay? So, and furthermore, what do we know? So these partial derivatives are all continuous. So let's go back to that theorem really fast and look at the conditions. So suppose all of these are continuous. So we know that, we see that u, v, and u plus iv is continuous because u is natural log function and v is the theta function, and we know that this is continuous from the log video. And we know all these partial derivatives will be continuous because their denominators are never 0, because these are real numbers, and x and y being real, they can never be equal to 0. So they are continuous in our domain. So domain with a single valued branch of log z. And just a quick refresher, what does single valued branch domain mean? That means we take a domain with an array from 0 to infinity anywhere deleted, and we just take the rest of the complex plane except that array. Okay, so these are continuous, u is continuous, v is continuous, u plus iv is continuous. So Cauchy equations are also met. What does that mean? At z naught, f is differentiable at z naught with f prime z naught is equal to this. So we're good to go. We can go ahead and write this derivative down. So we do du dx plus I dv dx. So what's du dx? It is x plus x squared plus y squared, x over x squared plus y squared, plus I times dv dx. So it's going to be here negative y over x squared plus y squared. And that will be f prime of z. Now we can clean this up a little bit. So let me get a new piece of paper and we'll clean this up really fast. Let's just write down what we had from the previous video, previous page. We have, I'm going to clean this up. I'm going to write it as f prime of z equals x minus iy all over x squared plus y squared. Okay, x minus iy is another way to write what? The conjugate of z, because z is x plus iy. And x squared plus y squared is what? It's the modulus of z squared. We can clean this up even further with this relationship. Z times z bar equals modulus of z squared. And the reason for that is because z is x plus iy, z bar is x minus iy, so we have x squared plus y squared, which is modulus of z squared. So that means we can rewrite this modulus z squared as z times z conjugate. So this is equal to z conjugate over z times z conjugate. Z conjugate cancels. We have 1 over z. Final answer. So after all that work, we have proved that log z prime equals 1 over z. And that's the power of Theorem C. So proof to Theorem C, click right here, you'll get the proof. And the final thing I wanted to note is that Theorem A and Theorem C are linked. Let's take a quick look at them before we end the video. So let me find my Theorem A. Here it is. So Theorem A says, suppose f equals u plus iv is analytic on D. So the supposition was that this is analytic on D. Well, what is the conclusion of Theorem C? Theorem C conclusion is that this is analytic at z0. So the conclusion of Theorem C is that something is differentiable, but the supposition of Theorem A is that something is differentiable. Now, what is the conclusion of Theorem A? The conclusion of Theorem A is that Cauchy-Riemann equations are met. What is the supposition of Theorem C? Supposition of Theorem C is that Cauchy-Riemann equations are met. So these are just converses, kind of. So they're not exact converses because this also has something about continuity, but the general gist of it is that Theorem A says that if something is differentiable, then Cauchy-Riemann's equations are met. And Theorem C says that if Cauchy-Riemann equations are met, then it's differentiable. So we can kind of go both ways. It's biconditional. So make sure you check out those proofs if you want more in-depth on Theorem A, B, and C. And until next time.